Article 250.4 of the National Electrical Code 2002 states that non-current carrying metallic enclosures shall be grounded. An approved means of grounding shall be provided for grounding such enclosures. The purpose of requiring grounding conductors in phase carrying conduits is to ensure that the conduits are at the same electrical potential as the equipment they enclose. This prevents the conduits from becoming a pathway for ground fault currents, which could create a hazard by energizing exposed metal surfaces or causing interference with other systems. While a grounding grid can provide a path for ground fault currents, it may not be sufficient to maintain the same electrical potential throughout the system, especially for conduits that are connected to multiple pieces of equipment or that run through different areas of the building. Conduit grounding conductors provide a direct path for ground fault currents to flow back to the grounding grid, ensuring that the conduits are at the same potential as the equipment they enclose. It is true that multiple ground loops can create noise in systems. However, the proper design and installation of grounding systems can minimize this effect. By using low-impedance grounding conductors and ensuring that connections are tight and secure, noise can be kept to a manageable level. Considering the above points, the requirement for grounding conductors in phase carrying conduits aligns with Article 250.4 of the NEC 2002. While it may create some potential for noise, the benefits of protecting against ground fault hazards and ensuring proper system operation outweigh this potential drawback. The grounding grid serves as a primary grounding electrode system, providing a low-impedance path to earth for fault currents. It is crucial for personnel safety and equipment protection. The grounding grid typically consists of interconnected bare copper conductors buried in the earth, supplemented by ground rods or other grounding electrodes. Its purpose is to limit the voltage rise during ground faults and to provide a path for fault current to return to the source, facilitating the operation of overcurrent protective devices. Conduit grounding conductors, also known as equipment grounding conductors, are installed within the conduit along with their phase conductors. These conductors are typically copper or aluminum and are sized according to the requirements of the NEC, specifically Table 250.122. Their primary function is to provide a low-impedance path for fault current back to the source in the event of a ground fault within the conduit or connected equipment. The equipment grounding conductor helps to quickly clear the fault, minimizing the potential for electrical shock and equipment damage. The NEC requires that all non-current carrying metallic enclosures, including conduits, be grounded. This requirement is intended to prevent these enclosures from becoming energized during a ground fault. If a fault occurs and a metallic enclosure is not properly grounded, the enclosure can become energized, posing a significant shock hazard to anyone who comes into contact with it. The equipment grounding conductor provides a path for the fault current to flow back to the source, tripping the overcurrent protective device and energizing the circuit. Ground loops can occur when there are multiple paths for ground current to flow, creating circulating currents that can introduce noise into sensitive electronic equipment. While it is desirable to minimize ground loops, the primary concern must always be safety. The NEC requires the use of equipment grounding conductors to ensure that metallic enclosures are properly grounded, even if this creates the potential for ground loops. To mitigate the effects of ground loops, several techniques can be employed, including the use of low-impedance grounding conductors, star grounding configurations, and isolation transformers. The connection between the 480-volt switcher and the step-up transformer typically involves multiple parallel conduits to accommodate the high current carrying capacity required. Each conduit must contain an equipment grounding conductor sized according to Table 250.122 of the NEC. The equipment grounding conductors should be securely connected to the switchgear enclosure, the transformer enclosure, and the grounding grid. The use of multiple equipment grounding conductors in parallel provides a redundant grounding path, further enhancing safety and reliability. The electrical inspector is responsible for ensuring that the electrical installation complies with the requirements of the NEC and other applicable codes and standards. The inspector has the authority to require that all non-current carrying metallic enclosures be grounded, including conduits. This requirement is based on the NEC and is intended to protect personnel and equipment from electrical hazards. While the grounding grid provides a general grounding path for the facility, it does not eliminate the need for equipment grounding conductors and conduits. The equipment grounding conductors provide a direct, low-impedance path for fault current to flow back to the source, ensuring that overcurrent protective devices operate quickly and effectively. To minimize noise, consider the following measures. Firstly, use low-impedance grounding conductors to reduce voltage drops in circulating currents. Secondly, implement a star grounding configuration where all grounding conductors are connected to a single central grounding point. Thirdly, use isolation transformers to isolate sensitive electronic equipment from ground loops. Fourthly, ensure that all grounding connections are tight and secure to minimize resistance. Fifthly, use shielded cables to reduce electromagnetic interference. The NEC provides specific requirements for the sizing and installation of equipment grounding conductors. Table 250.122 of the NEC provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. The equipment grounding conductor must be connected to all metallic enclosures and equipment in the circuit. The grounding grid should be designed and installed in accordance with the requirements of IEEE Standard 80 Guide for Safety in Alternating Current Substation Grounding. This standard provides detailed guidance and the design of grounding grids to ensure that they provide adequate protection against ground faults. The grounding grid should be sized to handle the maximum fault current that could occur at the facility. The grounding grid should be connected to all major pieces of equipment, including generators, transformers, switchgear, and motor control centers. The grounding grid should be supplemented by ground rods or other grounding electrodes to improve its effectiveness. In summary, the requirement for grounding conductors in phase carrying conduits is in line with Article 250.4 of the NEC 2002 and is intended to protect personnel and equipment from electrical hazards. While the grounding grid provides a general grounding path for the facility, it does not eliminate the need for equipment grounding conductors and conduits. The equipment grounding conductors provide a direct, low-impedance path for fault current to flow back to the source, ensuring that overcurrent protective devices operate quickly and effectively. By following the requirements of the NEC and implementing appropriate grounding techniques, it is possible to minimize the potential for electrical shock and equipment damage. The grounding system is not just about meeting code requirements, it is also about ensuring the safety of personnel and the reliable operation of equipment. A well-designed and properly installed grounding system can prevent electrical shocks, reduce equipment damage, and minimize downtime. Therefore, it is essential to take the time to design and install a grounding system that meets the specific needs of the facility. Consider the type of equipment being used, the potential fault currents, and the sensitivity of electronic equipment to noise. By carefully considering these factors, it is possible to create a grounding system that provides a safe and reliable electrical environment. In addition to the NEC, there are other standards and guidelines that provide information on grounding practices. IEEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, provides detailed guidance on the design and installation of grounding systems for a variety of applications. This standard covers topics such as grounding electrodes, grounding conductors, equipment grounding, and bonding. It also provides information on how to minimize noise and interference in sensitive electronic equipment. Another useful resource is the National Electrical Contractors Association NEC, which publishes a variety of guides and standards on electrical installation practices. These guides cover topics such as grounding, bonding, and wiring methods. They provide practical advice on how to install electrical systems in accordance with the NEC and other applicable codes and standards. When designing and installing a grounding system, it is important to consider the specific requirements of the equipment being used. Some equipment may require special grounding techniques to ensure proper operation and to prevent noise and interference. For example, sensitive electronic equipment may require isolated grounding systems or shielded cables. It is also important to consider the environmental conditions in which the equipment will be used. In corrosive environments, it may be necessary to use special grounding electrodes and conductors to prevent corrosion. In wet environments, it is important to ensure that all grounding connections are waterproof. Regular inspection and maintenance of the grounding system are essential to ensure that it continues to function properly. Grounding connections should be checked periodically to ensure that they are tight and free of corrosion. Grounding electrodes should be tested to ensure that they are providing adequate grounding resistance. Any damaged or corroded grounding component should be replaced immediately. By performing regular inspection and maintenance, it is possible to identify and correct potential problems before they lead to electrical hazards or equipment damage. The grounding system is a critical component of the electrical system and should be treated with the same care and attention as any other critical component. In addition to the technical aspects of grounding, it is also important to consider the human factors. Electrical workers should be properly trained on grounding practices and should be aware of the potential hazards associated with working on electrical systems. They should be provided with the necessary personal protective equipment, such as gloves, safety glasses, and insulated tools. They should also be trained on how to identify and correct potential grounding problems. By promoting a culture of safety, it is possible to minimize the risk of electrical accidents and injuries. The grounding system is not just a collection of wires and electrodes, it is a critical safety system that protects personnel and equipment from electrical hazards. Therefore, it is essential to take the time to design, install, and maintain a grounding system that meets the specific needs of the facility and that complies with all applicable codes and standards. A 480-volt switchgear serves as a central distribution point for electrical power within the facility. It typically contains circuit breakers, fuses, and other protective devices that are used to protect downstream circuits and equipment. The switchgear must be properly grounded to ensure that it is at the same electrical potential as the grounding grid. This prevents the switchgear enclosure from becoming energized during a ground fault and reduces the risk of electrical shock. The step-up transformer is used to increase the voltage of the electrical power from 480 volts to a higher voltage for transmission or distribution. The transformer also must be properly grounded to ensure that it is at the same electrical potential as the grounding grid. This prevents the transformer enclosure from becoming energized during a ground fault and reduces the risk of electrical shock. A connection between the 480-volt switchgear and the step-up transformer typically consists of multiple parallel conduits. This is done to increase the current carrying capacity of the connection and to reduce voltage drop. Each conduit must contain an equipment grounding conductor that is sized according to the requirements of the NEC. The equipment grounding conductors should be securely connected to the switchgear enclosure, the transformer enclosure, and the grounding grid. This provides a redundant grounding path and ensures that the connection between the switchgear and the transformer is properly grounded. The electrical inspector plays a crucial role in ensuring that the electrical installation complies with the requirements of the NEC and other applicable codes and standards. The inspector reviews the electrical plans, inspects the electrical installation, and witnesses testing to verify that the installation is safe and compliant. The inspector has the authority to require that any deficiencies be corrected before the electrical system is energized. The inspector's role is to protect the public from electrical hazards and to ensure that the electrical installation is safe and reliable. In conclusion, the requirement for grounding conductors and phase-carrying conduits is a fundamental safety requirement of the NEC. The grounding conductors provide a direct, low-impedance path for fault current to flow back to the source, ensuring that overcurrent protective devices operate quickly and effectively. While the grounding grid provides a general grounding path for the facility, it does not eliminate the need for equipment grounding conductors and conduits. By following the requirements of the NEC and implementing appropriate grounding techniques, it is possible to minimize the potential for electrical shock and equipment damage. The grounding system is a critical component of the electrical system and should be treated with the same care and attention as any other critical component. Always consult with a qualified electrical engineer or electrician when designing and installing a grounding system.